this work is done in Professor Lin Xin's group at Academia Sinica, and our group members are Liu Yanfu, Yao Liangzi, Chen Yueting. So, okay. So let me first state what's the goal of machine learning plus DFT or ab-initio calculations. So we know that machine learning algorithms have the ability to learn universal, do you represent any universal smooth functions from a well-represented data set. So this is called the universal representation ability of machine learning algorithms. So we want to make use of this ability to design a deep tensor neural network that will allow us to capture or to model the output of a DFT calculation from input parameters such as atomic positions and maybe other quantum mechanical or quantum chemical insights into the system. So the main reason for this is that DFT calculations have a cost of order of n cubed, where n is the size of the system or number of atoms in the system. However, because all deep tensor neural networks are based on matrices, so if we are able to reduce, we are able to map, use a deep tensor neural network to map a DFT calculation, then that reduces the calculation cost from order n cubed to order n squared. Okay, so what's the output that we would like to get from a machine learning model? So basically, the whole purpose of a DFT calculation and also the machine learning model, which we hope to replace or complement our DFT calculations, is to calculate the physical properties of the system. So the basic properties are the total system energy, the forces acting on each atom, as well as dipole moments of each atom. So these can be used to calculate a number of physical properties. For example, atomic force can be used to calculate the phonon spectrum, and the atomic dipole can be used to calculate the electric susceptibility. So these will be very important because we want to, the final state of our workflow is to feed these atomic force and dipole outputs from the machine learning model or DFT calculations into molecular dynamics simulation, which we will then use to simulate heat and electric various quantum materials that are of great technological importance, such as thermoelectric materials, piezoelectric materials, and also maybe batteries. So that's the main focus of, that's the main motivation as well as the main goal of our work. Okay, so let me briefly introduce what's called a deep tensor neural network. So the first deep tensor neural network in the context of materials simulation was proposed by Bella and Parinello group. So it's commonly called the Bella-Parinello DTNN or the BP-DTNN. So the inputs for this system are the interatomic distances. Sorry, let me see if I can find my mouse. I don't know if Microsoft Teams has a mouse. So I can. Jim, is there a mouse? No,
I don't think so, and I think Keynote may not. Is the Keynote?
Oh, Keynote's issue. Yeah. Okay, that's.
Yeah.
Okay. So,
I remember we cannot use the pointer in Keynote.
Yeah. Okay. Okay. So on the left hand side we see R1 alpha, R2 alpha to Rn alpha, and so 1, 2, 3 labels the atom that we are trying to feed into the system. So we have 1 to n atoms, and alpha represents XYZ. So that's just the Cartesian coordinates for the atomic positions for the system. So we feed that into the system, and then we calculate symmetry. So in BP-DTNN, what they use as their basis set are symmetry-invariant functions G, which I'll describe later. So these symmetry-invariant functions respect the rotational symmetry of the system, and then so that will capture the interatomic pair environment of each atom. And then after constructing these symmetry invariant functions, they are then fed into a feed-forward neural network SI. So the energy of each atom, E1, E2, E3, all the way up to En, is represented by a single neural by n different neural networks SI. They all have the same architecture, which I'll show again later. So by taking the input G, these feed-forward neural networks will then map the energy of each atom E1 or EI, and then the total energy of the system is obtained by summing up simply by summing up E1 to En. All right.
So can I ask a question?
Yeah, sure. Go ahead.
So what do you mean by the index, the subindex 1, 2, 3? Is that does that mean it's subsystem or?
I mean, so 1, 2, 3. Let's say on the right hand side, E1, E2, E3. It just refers to the energy of each atom in the system. So
each
E1
atom.
refers each atom.
So they calculate the energy of each atom separately, and then come together. So there's no interaction between atoms, or?
So that's supposed to be so the interaction between the atoms is supposed to be captured in the mapping on the left hand side, where all the so we have R alpha of 1 to n, and all these are all mapped to G1 mu and G2 mu. So you can see the arrows on the left hand side basically means that all the interatomic positions are mapped to G1 or Gi mu of each atom. And then
you mean the interaction had been, the information of the interaction had been embedded into G1, G1, G2, G3, right?
That's right.
I see. Yeah. Thank you.
No problem. Yeah, feel free to interrupt with questions if you guys need to. So I think that would instead of saving the questions all the way to the end, so that would. So let me just point out the reason why it got such a big interest in the field was that BPDTNN got demonstrated an order of magnitude improvement in speed over ab-initio MD, which is DFT plus MD. So that would greatly speed up the scale of our simulations. Okay, so later on I'll show a bit show some brief rough order of magnitude figures for various technologically important applications. Okay, so this is some technical details. So what's G1, G2? The symmetry invariant functions that they use in these papers have two components. G1, which is the interatomic radially symmetric function, which basically is which is basically some Gaussian functions times some cutoff distance. So G1I is the sum of over all pairs that are next to the atom I, and we scale it as a Gaussian times some cutoff distance. So basically, the cutoff distance RC defines a neighborhood or a cluster around the atom I, that around which you construct all these this G1. Basically, say we have a system of a million atoms, but we only include say 100 atoms or within each local cluster, because the atomic bonds don't stretch up to a million atoms in length. So that's why we introduce this FC cutoff, and then there's a smooth cutoff. So there's some cosine function within for Rij less than some radial cutoff distance RC, and then beyond RC is just 0. Now we also need to take into account the angular information between the atoms. So G2, the other function that they use is the angular symmetric function, which is basically used to encode all the angular informations between 3 atoms ijk. So if you look at the first line of G2, you see that it's a 1 plus lambda cosine theta ijk, which is the angle between so if you imagine an atom I, which forms a triangle with ijk, and then theta ijk is just the angle between the angle at I between atom j and k. So G2 basically maps up all the angular information between the atomic pairs within this cluster. Now, finally, after now that we have gotten G1, G2, so what do? We feed it into the feed-forward neural network SI, and SI will give us EI. So the deep tensor neural network structure is basically so if we start, so let me just explain what notation here means. F1A and F2A are the different layers. So we have two layers here, and they are activation functions. And then W is a matrix with some weight. And W1 of mu J is the first neural network layer. So it's a matrix times G mu, which is the input function. And then W1 subscript 0 is some bias term. Basically allows us to shift the weights of the bias weights of the system. So you feed that. So it's basically a matrix. So it's W of G, W times G plus some weights, and then after you act on it with this matrix, then there's an nonlinear activation function F1. So the main reason why neural networks work is that apart from their matrix structure, the reason why they are able to have this universal representation ability is because each neural network layer has a nonlinear mapping. It is precisely this nonlinear mapping that allows the neural network to capture any universally smooth function from a well-represented data set. And after that, you act on it again on the second layer with another matrix W2 with some weights W2 of 0, and then you have another nonlinear activation function F2, and then you finally you get your atomic energy. And so the parameters that are trained in this neural network are the weights of W1 and W2. So in the backpropagation process of the neural network, what ends up being trained are the weights W. Okay, so how does the entire workflow go? So the workflow starts with we construct a DFT plus MD data set. So we use DFT to run some crystal configuration. We get some energies and some dipoles and some forces. At the same time, we feed it into MD and run it at some VE at some grand canonical ensemble. So we maybe allow the temperature, or we allow the chemical potential or the number of atoms in the system to fluctuate a little bit, and then we evolve the system in time with at some temperature or some fixed energy, and then you'll calculate and you get new configuration, and then we calculate the DFT ground state again. So DFT plus MD will give us a grand set of configurations with some corresponding energies, which we then use as the training data set that we feed into the BPDTNN. So we train the BPDTNN to learn what is the energy and the force, and then we feed it back into MD simulations. And the MD simulations so MD simulation is basically a classical simulation that is basically basically all it does is it uses Newton's laws, or just classical mechanics to simulate the motion of the atoms. And then so what it needs are the forces acting, and the forces and potential energies of acting on the different atoms, and then it will evolve it in time, say for maybe 1 nanosecond or 1 picosecond, and then you come up with a new configuration. So the checking process is you take these new configurations and you calculate and use DFT to calculate them again, and then if the DFT calculations of these new configurations give the same energy or similar energy as the BPDTNN prediction, then that means that BPDTNN has learned these configurations well. But if it doesn't, so if the difference in energy between the DFT calculations of these new MD configurations differs significantly from the BPDTNN prediction, then that means BPDTNN has not learned these new configurations well. So we feed these new configurations back into the training data set, and then we repeat the whole process. Okay. So just to show what are the results that some of the results that they got in BPDTNN. So on the left hand side, we see the difference in energy between the DFT calculations and the neural network prediction. So this is in electron volts per atom, and then we see that it's about 5 milli-electron volts, which is very good. 5 milli-electron volts is about what about 60 Kelvin. So that's way below room temperature. So for many, it's good enough for many, I guess, for materials exploration. And on the right hand side, we see that we see the distribution function of. So they simulated silicon at 3000 Kelvin, which is near its melting point, and then they calculated the distribution function of this silicon, and you can see that the black one is DFT and the red one is neural networks, and the others, Bazant, Lenoski, Tensor, they are all empirical potentials that people have used in quantum chemistry and material science. And you see that the red and the black are the closest, which means that neural network has learned the potential energy and the forces well for silicon, close to its melting point. So that's a good check. Okay, so that was the first deep tensor neural network.
Hi.
To
I have a question. Can
Sure.
you go back to the previous slide?
This one?
So I was wondering, yes, thank you. So the MD simulation is the output from the BPDTNN, right?
Yes, MD simulation. It takes output from the BPDTNN.
So I was confused. So this MD simulation is something from the BPDTNN, but when you say like this, doing the DFT calculation of this MD simulation, and then if this is like far away from the correct answer, then you put it into the training state to training again.
That's right.
Isn't this is something from the like bad prediction? But why you just calculation and throw it to the training state?
The bad prediction means that the neural network has not learned the potential energies and the forces for that particular configuration well. So we use DFT. So now, so this is in comparison to the correct result, which is our DFT calculations. So we take the correct prediction, or we take the correct potential energies and the forces from the DFT calculations of these poor configurations, and then we feed that back into the training data set. So we actually we're correcting the wrong results, and then we are adding the correct results from the DFT calculations of these poor configurations back into the training set. Do you understand what I mean?
Yeah. But I think I was thinking maybe the correct result is already in the MD data set.
The correct result.
Maybe, I mean, is this bad prediction is from some input and label maybe, and so I was thinking there maybe they are already a pair, and so it just give you a bad prediction. So but there still there's some correct answer is already in the data set.
No. So for each atomic, for each particular atomic configuration, there is a correct energy and force label from DFT, and so what BPDTN, what the tensor neural network does is, instead of calculating, so the DTNN is supposed to approximate or simulate the DFT result based on based on these some atomic inputs, and then it will give a prediction of the energy and force that is supposed to be close to the DFT result. But the DTNN or the neural network may not have captured all of the phase space or configuration space of all the phase space of all the different atomic configurations well enough. So, for example, let's say, so you can think of it as the true potential energy landscape and force landscape of the let's say silicon for all different possible atomic positions of silicon is some complicated structure, and this can be calculated by DFT. And then but it's not possible to map out this entire complicated structure for a huge system because it's too expensive. Say even so, what we do is DFT is only able to calculate a small number of the phase space, and then you use a limited volume of this phase space to train the neural network, and then hope that it can predict the energies and forces of other configurations in the entire phase space that's outside of this training data set phase space. And then when you run the MD simulation, and then you check, and then you see that, and then the MD simulation basically will explore all of this phase space, and then when it comes up with some new configurations, you will check with DFT to see if it's correct. And if it's not, then you have to do the DFT calculations for this new sub-region of the phase space, and then feed it back into the data set. Do you understand?
Okay. I think I roughly got the idea. Thank you.
Okay, no problem. Okay, so another very successful application of another very successful model of this deep tensor neural network is this deep potential MD, or what we call deep MD, which is by a Princeton Berkeley group, which won the ACM prize, ACM Gordon Bell Prize. So what they do here is again quite similar. So if you look at the the left diagram, so figure 2, what it shows is that we again have the atomic positions R1 to Rn, and then they calculate the internal atomic positions Rij, and then you feed it into. However, so the difference here is instead of using rotationally symmetric invariant functions G in BPDTNN, they feed it into a series of neural networks Dij. So Dij is will produce some rotationally invariant as well as permutationally invariant descriptors, which are fed into hidden layers, these blue feed-forward neural network layers that will finally model or estimate what the atomic energy of each individual atom is. So that's the entire architecture of the system. Okay, so now let's look at the figure on the right hand side. Figure on the right hand side describes what actually happens. Okay, so the sub figure A will basically it tells you that that's the entire architecture of the system. And then what actually happens is, okay, if you look at the figure 1B on the right hand side, we have the input atomic positions Ri. So what's Ri? Ri is XYZ, and multiplied by, and then they add another column S. S is basically 1 over Rij. It's because we need to. That's the radial part of the information. Okay, so that's what is defined as R tilde, and then you take R tilde, and then the descriptors are formed by G times R, G transpose, G1 transpose times RR transpose times G2. and G1 and G2 here are what they call embedding matrices. Okay, so and G1 and G2 are part of the machine learning model. So the parameters or the weights of these matrices in G1 and G2 are learned by the system, and then they show in figure C what are some of the values of G1 and G2. Then you can basically think of it as some form of orbital the radial distribution functions of some orbital wave functions. Okay. And it's C1. So yeah, okay. So if you look at C1, you can see that there's some peaks at some fixed positions. So that sort of corresponds to the atomic positions, the radial distribution of the atoms in the cluster that's centered at I. So you can think of it as at maybe 2.5 angstroms there's a shell of atoms, and then at 4.5 angstroms there's another shell of atoms, and for the smaller peaks at 3.5 angstroms and maybe at 5.25 angstroms and at 5.75 angstroms there's a smaller shell of atoms. So that's basically some physically intuitive idea of what G does. G sort of captures the distribution of the atoms in the cluster around its center. Okay. Okay. Now, what so RR transpose? So actually there's some guiding principles to the way they construct G1 transpose times RR transpose times G2. So as I mentioned earlier, we have to we want the system to be permutation invariant. So what does it mean by permutation invariant? Permutation invariant means, okay, we have let's say 100 atoms as our input, 1 to 100. Okay, but person A and person B may not input these 100 atoms in the same way. So maybe person 2 will exchange atom 1 and atom 2. So it will flip. The order of the data input gets flipped. So 1 and 2 gets flipped, or 3 and 4 gets flipped. So we want to make sure that despite these permutations in the data entry, the network model that we train is invariant or robust under these permutations. So this is called permutation invariant. So this was first proposed by Google's one of Google's research group. And
if that's a permutation invariant, which means that you ignore the spatial information, right?
You ignore the specific.
Not specific, spatial.
Yeah, that's right. You include the interatomic position. You include the interatomic spatial position, but you are insensitive, or you ignore the specific particular position Ri. So you basically looking at Rij, but you basically not you don't care about Ri. That's right. You ignore the spatial information of the absolute position of each atom. That's right. Yeah. So that a related concept is called permutation equivariant. So permutation equivariant would then be you are sensitive to the particular position of each atom Ri. So if you exchange I and J, or I and I prime, then the output energy EI and EI prime will get switched as well. So that's called permutation invariant, but a permutation equivariant. But permutation invariant means that, like what you just said, we do not care about the absolute position of a particular position of a particular atom, and we keep only the we only keep information about the interatomic position Rij. Yeah, so the way you do this is again by matrices. So they constructed what they call an attention map, and then the main information is at the bottom. If you look at the equation at the bottom, MT is some activation function sigma. So basically, it's Q times W. Just ignore the WQ and WK and the WV. They are just weight functions. So it's basically Q times K transpose times V. So K transpose times V. So K, if you look at K and V both take input O or T, and as their input information. So OT basically labels the row of the matrix K and the row of matrix V. But we are multiplying K transpose times V. So when you switch O of T to O of T prime, so K will have a change of index from T to T prime, but V will also have a change of matrix from T to T prime. So when you multiply K transpose times V, it is invariant. So it's insensitive to switch in the absolute position of the atom. So that's how they construct. So that's how you get a permutation invariant attention map. So the way they did this in DeepMD is the same thing. They did G transpose times R. So G transpose is a function of Rij, and R is of course a function of Rij. So if we switch I to I prime, then G will have a switch of its rows, and R will also have a switch of its rows. So G transpose times R will be permutation invariant. And then the reason why they have a G1 and G2 is that they want to basically they want to abstract out a smaller number of features from the spatial positions. So basically, G1 is a big matrix, and G2 is a smaller matrix. And the hope is that you are only using the information from the smaller matrix G2 to feed into the neural network. Okay, so those are some technical details that we can talk about another time. Okay. Yeah.
May I ask a question?
Yeah.
In the permutation group you are mentioning here, are you mentioning to the space group of the particular lattice? Are you implementing the symmetry of the lattice, or are you implementing other symmetry? Just permutation.
Oh, we're just doing permutation. Great. Yeah, thanks for that question. We so actually in the second part of the talk, we will talk about one group of the crystal lattice. Yes. So that's thanks for the question. It's a good lead up to the second part of the talk. So if you can just hold your attention for a little bit, we will get to that part a little bit later.
Okay, thank you.
Yeah, thanks. Okay, so what's the success of DeepMD? Basically, the success is they managed to simulate hundreds of millions of atoms on the Summit supercomputer. So on the left-hand side, we see they simulated water as well as copper as an example. So water, you can see they scale up from 42 million to 679 million atoms, and the number of flops that was executed on Summit was from about 5 or 10. So depending on the precision they use, it's double or mix. So let's just take the green. Let's just take the green one for So they went up from about 8.8 petaflops up to 140 petaflops, and the number of nodes that they use, number of GPU nodes they use, went from 285 to 4,560. So that's that's a pretty I think that's a pretty significant accomplishment. And then for copper, they went up from 8 million copper atoms to 127 million copper atoms, and the number of petaflops that they executed was 10 petaflops up to 160 petaflops. Basically, it shows that the system scales well, that their architecture scales well on a supercomputer, and then they can and they are by increasing the number of nodes and number of flops, they are able to scale to larger and larger systems. And right, so on the right hand side, we what we see is a nanocrystal of copper, nanocrystal of copper, and purple, yellow, and cyan represents the atoms in the grain, which is the nanocrystalline structure, atoms in the grain boundary. So basically, these are nanocrystalline or they're polycrystalline. So you have granular structure, and then the purple ones are in each micro or nano grain. And then between the grains, you have grain boundaries, which are represented by the yellow atoms. And then there's structural faults or stacking faults or fractures, and these are the ones in cyan. The one in like dark green on the right hand side, if you can see there, like a couple of stripes running through the diagonal along the diagonal. Yeah, I hope you guys can see that. It's kind of cool. So basically, by simulating 100 million copper atoms, they are able to simulate the basically a pretty big 15 nanometer nanocrystalline grain, which is decent size, and they are able to see structural faults, which will allow us to do material properties, stress, strain, tensile, whatever. So that's the order of magnitude that we need for this structural simulation. So for this, they won the 2020 ACM Gordon Bell Prize, and so basically this is taken from their presentation, their talk. Basically, what they showed is that AIMD, if you look at the upper right hand side, AIMD takes about 0.01 second, 0.01 second per MD step per atom. Whereas, whereas deep MD, if you scale up on the Summit supercomputer, it takes only 10 to the minus 9 seconds per step per atom. So it's orders of magnitude improvement compared to usual AIMD. It's like and the reason we need to do this, as I suggested, as the previous figure suggested, is that if you look at the bottom right hand table, it shows that if you want if you want to simulate dynamic fracture, the time scale that you need is 0.1 nanoseconds, and the size of the system is about 100 million atoms. And then say we are interested in this solid liquid interface, say for a battery electrode, then the time span that we need to simulate for these electrolyte reactions is 100 nanoseconds, and the system size about 1 million atoms. So all these become large system size problems that we need to be able to tackle, and that's DeepMD's contribution. Okay, now the third neural network structure that I'd like to introduce is called SCHNet. It's named after the author Schutnet. So here, it was initially proposed for molecules and some simple materials. So they are a chemistry group, and then they focus on this neural network for molecules. So if you look at the right-hand side, what they're showing is a single carbon atom on the first row, and then they're showing the sort of the radial distribution function around the carbon atom, which is symmetric, or it's a circle. It's radial because there's only one atom in the middle of a vacuum, so it's of course a circle. And then then you put carbon in a diamond lattice, and then you stack it up, and then some neural network representation of the orbital wave function looks like this hexagonal structure that you have for diamond and also for graphite. So they are able to show that their neural network sort of reproduces the crystal symmetry of the system and the molecular shape. So this is their early. This is one of the early versions, and then they have, of course, later works that are a bit more sophisticated. So the way it works is that. So okay, now let's look at the left-hand side. So the way it works is the architecture of the system is all the way on the left. There's a green layer which embeds the information of each atom and its chemical species as a series of vectors. So R plus some nuclear charge information, and then it's fed into an interaction block, the yellow block. So what does the yellow block do? The yellow block basically takes the information x, well, so R1 to Rn, and then it does a convolution on all these atoms using the filter generator, this orange neural network. This orange neural network basically does a real space convolution of the atoms, which is what generates the pretty pictures that you see on the right hand side. It's W that will capture all the spatial information. And how do you get W? W again is some. Okay, so the way you get W is here. Okay, so W is a continuous convolution filter that takes the. So okay, let me phrase it another way. So we start with the atomic. So look at the right hand side. Look, we start with the atomic positions R1 to Rn, and then we map that to some radial basis functions at different centers mu k. So ek of Rij is some exponential function, some Gaussian function, e to the minus gamma of I minus Rj minus mu k squared. So it's and then mu k is where the Gaussian function is located. So basically it tells us whether it's located at the center, or as you know here, is it located at the next ring or the third ring or the fourth ring. So basically mu k tells us where these rings are located. And then the weights of these Gaussian basis functions will tell us what the symmetry of the system is. So if you look at the first row on the top, you can see some are brighter and some are darker, and that basically tells us which mu k is important and which one is less important. So after generating these radial basis functions, you feed it into a neural network that gives you W, and basically the W is some relative weighting of these these radial basis functions. And that will, like what I said, they'll tell you what are the important rings that you want to keep. And then after getting these W's, you do what they call a continuous convolution, which is W times L, this matrix times L, and then that will filter out the relevant information for the relevant spatial information, and then feed that back into the XL for the next step. So XL for the next step. So XL. So when you go through each yellow block, you are basically doing each one layer of this continuous convolution filter, and then you get the next dressed. You get the next XL plus one, which is a dressed descriptor, dressed spatial information, or rather the spatial information for each atom I based on which is dressed by its neighboring atoms. So the physical meaning of XL is what is the radial distribution around atom I based upon its local environment, which is dressed by WL. Okay, so having now find, and then you after, okay, so you do this a few times, and then you get XL, maybe XL, L equals to maybe 10 or 20, and then you feed it into another neural network and you get E. So the second part of the work is similar to the second part of the work is similar to all the neural networks that we have seen. So you predict the energy of the molecule based on these dressed descriptors, and then so they show their results. So the nice part of the work is that they're able to get some neural network representation of the molecular orbitals. So here we see benzene, toluene, methane, pyrazine, and propane, and it captures the molecular orbitals pretty well. And then on the left hand side, what it shows is how does the energy prediction of this SCHnet compare to to other tensor neural networks, DTNN. So DTNN here, so I can't quite remember what GDML means. DTNN here refers to BP-DTNN, the very first Baylor-Parinello network. So they show that the difference between their SCHNet calculation and DFT is about this is 0.08 calorie, about basically about 0.1 kilocalorie per mole, which works out to about I think 1 kilocalorie is about 40 MeV. So this 40. So this is about, yeah. So it compares favorably to BP-DTNN. So it's maybe about 20 MeV or 10 MeV. So it's again not too bad. Okay. So any questions so far? If not, you guys need a break. So the second part will be about what one of the members asked. Earlier about the point group of the crystals that, and then that's what we'll focus on in the second part of the talk. Okay. So if you guys are okay, then okay. So as we all know, crystals have space group symmetry. So space group symmetry is made up of point group plus this translational or sublattice, translational, and reflection symmetry, as well as maybe some inversion. So if we just focus on the simplest case, which is just a point group symmetry. So we want to construct. So one of our ideas right now is to construct a point group symmetry basically based on point group symmetry, construct a neural network that is that respects point group symmetry. So first let us understand what is point group symmetry. So let me use the simplest example, C4V. C4V means it's a square lattice, which is a square lattice. So square lattice is invariant under rotation, 90-degree rotation, 180-degree rotation, also reflection. Okay, so let me just explain what it means here. So what you're seeing in the table is the character table. So the top row represents the different classes. So each class, so for a point group C4, let's say a square lattice, there are different transformations that we can do in C4. So we have E, which is identity, 2C4. C4 means rotation by 90 degrees, 2 pi over 4. So it's pi over 2. So we have two possible rotations around the z-axis. We have plus 90 degrees and minus 90 degrees. And then C2 is rotation by 180 degrees. And 2 sigma V. 2 sigma V here, sigma reflect, it's an axis located on the x-axis or the y-axis. So it's a vertical reflection mirror. And then so we have x and y, so we have two of them. And then also sigma D. And then sigma D is a mirror along the diagonal along x plus y and x minus y. So we have two of them. So each class, and then so these are the different transformations for a point group, or rather for a group. In this case, C4 group. And then we look at the different rows on the left hand side: A1, A2, B1, B2. So one basically means S wave. A2 is S wave with odd under inversion. So we normally don't see that. B1, B2 are D wave, and E is PX, PY. So just to give you guys an idea what it means. So if we look at B1 is x squared minus y squared. X squared minus y squared, if you look at the figure on the right hand side, what is x squared minus y squared? X squared y squared is a d orbital with its lobes along the x and y axis. And then, if you rotate by 90 degrees, it's a minus sign. If you flip by the mirror reflection along x and y, it's even. But if you flip by sigma D along the diagonal, then it's odd. So that's how x squared minus y squared transforms in the C4 in the C4 point group. And then same thing for xy. You can do all these transformations again, and then you find that it behaves in a similar way to x squared minus y squared. Except that reflection is a bit different. And then E group is a PX PY. So PX PY is a two-dimensional representation, and then and then PX PY. Of course, PX becomes py, and py minus becomes minus px, and the rotation, and all these can be represented by matrices. So the character table basically captures all the information about these transformations, and then the details we can talk about another time. So the whole point of it is that this is to, so this is just to tell you what a point group is for a simple two-dimensional case for C4 square lattice. Now, in general, we have three-dimensional lattices. So one of the more common groups that we find is the octahedral group, OH. And so the takeaway point from here is that if you look at the A1G row, we have x squared plus y squared plus z squared. That's S wave. And then EG means 2z squared minus x squared minus y squared, and x squared minus y squared. These are what we call the EG electrons, or the EG orbitals. Again, these are the d orbitals. And then the T2G are xz, yz, and xy. So these are another group of d orbitals that transform differently under the OH group. And then the p orbitals that we have, px, py, pz, they transform under T1u. So px, py, pz form another representation. So that's the take-home message that I want you to just get from this slide. Details we can talk about another time. So based upon these different representations, x squared plus y squared plus z squared, e.g. T2G and T1U, or p orbital, what we want to do is we want to do a neural network construction of these different representations, or these S wave, P wave, and D wave orbitals. So S wave is the simplest. S wave means nothing changes. So what do you mean nothing changes? That means it's R squared, or 1 over R, or in this case, S of R. S of R, as I mentioned earlier, is 1 over Rij. So we can use 1 over Rij as the prototypical seed for constructing our S wave. But then we need to feed it into a neural network. We feed it in a neural network, and this is represented by the matrix GSI. So what does GSI mean? GSI means it's the S wave matrix that will transform that will transform these radial functions or radial information into what we call a generalized S-wave orbital, psi Si. And then this information is centered at the atom I. And all the interatomic pair information is captured in Rij. So basically, what it means is we have, so S of Rji is basically 1 over Rji. So 1 over Rji basically is inverse of the interatomic position between the central atom I and all the other atoms in the cluster. And then say it'll be say the cluster is 100 atoms, so it'll be a vector of length 100, and then it'll be 1 over R, 1 over R for all these interatomic pairs. Then we take G, Si, and then we act it on this vector, and then this will construct our generalized S-wave orbital. And then on top of that, we have to put in information about the type of atom that we are looking at. Is it a hydrogen atom, or is it a uranium atom, or is it a iron atom? So atoms are differentiated by their nuclear charge. So we put in AZI. Zi is the nuclear charge. So we put in a prefactor that basically encodes information about the nuclear charge of the atom or the chemical species that we are looking at. So this gives us psi Si. So what I wrote here is basically the vector form, and then what are the individual matrix or vector entries. So that's just math. Okay, and then this S-wave orbital is again permutation invariant, because when we switch G and J prime, both the matrix G and Sji and S of RGI flip sign. So at the end of the day, this S wave orbital is invariant to flipping J and J prime. Okay, and then what's M here? So the matrix G is N by M1. So N is the total number of atoms, and M1 is the number of features that we want to extract out. So we can think of it as the atomic shells for this particular atom. So we know for an atom, so for simplest example, hydrogen, we have 1s, 2s, 3s. So M1 basically represents which shell which shell we want to look at. Is it the 1s shell, 2s shell, 3s shell, so on and so forth. So that's the physical picture of what we are trying to construct for these generalized generalized orbitals. So okay, so this is for psi si for the S wave. Now we can do the same thing for px, py, pz. So we use another neural network GP, and then we feed in the different x, y, and z indices, and then we get you will get our neural network representation of px, py, pz, or psi x, psi y, psi z. Okay. Okay. Same thing now. Having constructed an SP, now we need to construct the D wave orbital. D wave are quadratic functions, they're x, y. So again, we do the same thing. So we need to do x squared, y squared, z squared, x, y, x, z, y, z, and z squared. So the way we do this is we do x times x transpose, x times y transpose, x times z transpose. So same thing here. So we get this mxy. Okay. Then we need to apply our radial filters again. So we have psi, the D wave orbital psi d of xy is given by a GD1 times GD times M times GD. And then again, we multiply by the nuclear charge, AZ. Okay, so these are all math. So basically, the point here is we can construct we construct in the same way the D wave orbitals. Okay. Okay. So this is yeah. Okay. This is a bit of some technical detail. So we'll just skip that. Okay. So at the end of the day, what we do is we end up constructing. We have psi s, psi x squared plus y squared plus z squared. X squared plus y squared and z squared are the S wave the S wave like orbital that we construct from the D wave representations. Then we have the p electrons, and then we have the Eg electrons and the T2 Eg electrons. So we put all this together into one big vector, and then we to calculate the energy we construct. This will be our orbitals or our wave function, and then the next thing we need to construct is our Hamiltonian H, and then the H will be block diagonal. Then we'll have a psi HSS block, which is interactions between the S electrons, HSP, which is interactions between the SP electrons, and then the SEG, ST2G, so on and so forth. So all of this will become block diagonal, and then we can construct each of these blocks one by one. So how do we construct these blocks? So okay, now let's look at the HSS block. HSS block. So again, the Hamiltonian is by so Hamiltonian is Hamiltonian in this case is S wave, and then it's formed from all these S orbitals. So what we do is we take all the S orbitals for this cluster, and then we put it into one big vector, and then we feed it and then we have two channels. On the left channel is we feed just this huge vector into a feed-forward neural network, and then on the right, and then the other channel that we use is convolution convolution neural network layer. So we reshaped our so basically the feed-forward neural network knows that the reason we use the feed-forward neural network is that feed-forward neural networks have a very strong representation ability. They are able to represent, as I stated at the beginning, they have this universal representation ability. Now, then the reason why we use CNN or convolution neural networks is that convolution neural networks have been shown to be very, very effective in image recognition, pattern recognition, speech, and so on and so forth. Not speech, sorry, image image and pattern recognition for recognizing spatial correlations or temporal correlations. Okay, spatial so the Hamiltonian at the end of the day is interactions between orbitals on different atoms. So these are basically pattern recognitions at the end of the day. They are just interactions or pattern. So we feed in all this information about the orbitals sitting on all these atomic positions into this convolution neural network, and we let the convolution neural network learn what are the important patterns or the interactions or correlations between the different atoms. And then we finally feed all of this information into a feed-forward neural network, and then we project it into the SS symmetry channel, and that's how we get HSS. Okay, same thing. This is a bit, maybe you guys are getting a bit tired, but okay. So the other property that we are really interested in is application of an external field and thermoelectric effect. And when we apply an external electric field, we know that we will reshape the charge distribution of each atom, which is the dipole. So dipoles are basically from the p orbital, px, py, pz. So the way we model this dipole is we take the p orbitals, we feed it same thing into a feed-forward neural network as well as the CNN convolution neural network, and then we get an approximation for the dipole sitting on each atom, and then taking this dipole, this neural network representation of the dipole, we can construct the Hamiltonian for the system, which is the dipole times the external field plus some Onsager, basically some this back reaction effect. So these are basically some physics which we can talk about later on. But basically, we can construct the Hamiltonian construct corresponding to the dipole, and then we put all these Hamiltonians together as one big Hamiltonian H, and then we can calculate we can finally calculate the total energy for the system, EI, or we sum over EI, sum over I for the entire system. And then, okay, so that's basically the main structure of the main architecture of our model. And then what are the outputs that we want to predict? We want to predict force, which is the derivative of the energy with respect to R. We want to calculate the stress tensor, which is R cross F. And then we want to also calculate the dipole moment, which is the total dipole moment, which is the derivative of E with respect to external field. So these are the physical properties that we want to calculate, or we want to output from the machine learning model. And then, so we need to compare this with the DFT result. So the usual way to do this is you define a loss function, and then you look at the root mean squared error, and then you minimize this, and voila. And then you complete the entire training cycle, and then you just, as I mentioned earlier, you just keep looping in the DFT MD cycle, and then you just keep until finally you get a good convergence. So that completes our entire machine learning model. So okay. So after going all through all this, the take-home message is why do we want to use machine learning models? Because these algorithms, feed-forward neural networks, have this universal representation ability, and the matrix structure of these DTNNs has an order n squared cost, which is much lower than the order n cube of DFT calculations. So we get close to DFT accuracy, but at maybe 1 or 2, maybe even 3 times the order of magnitude improvement in speed. And then to do this, we have to optimize our input descriptors. So here we have proposed a point group symmetry based descriptors. And then the architecture of the model that we use is, one is the feed-forward neural networks, which have this universal representation ability, and then the other leg of the architecture is convolution neural networks, which are very good at capturing spatial correlations. So at the end of the day, after doing all this, what we want to predict is system energy, atomic force, dipole moment, and then you can use this to calculate more properties such as phonon spectrum, electric susceptibility, so on and so forth. And then the end goal of this is to feed all this information into MD, and then we can simulate all types of transport phenomena, such as thermoelectric behavior, piezoelectric behavior, and also maybe electrolyte, solid liquid interface physics, which is important for batteries. Okay, thanks.
Thanks, Jim, for today's talk. Is there questions from the audience?
I have a question about the permutation group.
Sure.
My question is, I understand the necessity of the space group, but for permutation group, you are focusing on the permutation between atoms or more atoms of the same species, right? So, but my question is, in the neural network representation, you already choose specific ordering of the atoms.
Yes.
So why do you need the permutation in the neural network? Because you already fixed the ordering of the position.
Yeah, because if you fix the position of the atom, then the weights of the matrix W or whatever W that will get tied to that particular input format of the data, particular data input format. So if you switch atom 1 and 2, then the weights of the matrix in the neural network will not correspond to the switch data input format. So if you switch the data input format, then you also have to switch the matrix the matrix row that multiplies this atom position. So that's the reason why. Otherwise, if you put in a particular permutation for your data input, and then you switch it, you permute it again, then your network will give you wrong results.
So, do you mean you are dealing with the permutation between the weight matrix, or you are also dealing with the permutation between the input?
Both.
Okay.
So it's only by flipping both that you are able to maintain permutation invariance.
I see. Thank you.
No problem.
I have a quick question. It's about the how do you define the loss function? Is a loss function like in your training process? Right.
The loss function is here. This is the loss function is defined right here. So it's the root. It's the squared error, not root mean square error. I'm sorry. So it's the squared error. It's for example, it's the energy minus the energy, neural network force minus the DFT force. The stress tensor.
Yeah. So this loss function, basically you can define this loss function before MD simulation.
Yes, of course. This is part of the MD. This is part of the ML, the machine learning model. Yes.
And then you feed this. You update in your parameter before MD, or I just don't understand how do
you fit before MD. You fit all the you train all the machine learning models before MD.
Okay, so the idea is that you use the machine learning to feed the to that the energy close to DFT, the energy obtained from DFT, then output this force or energy information to the MD simulation, and after the MD simulation, you can find that the delta E. If the delta E is bigger than something, then you will add new sample, new Y.
That's right. That's right.
Put to a data set, and then redo that again.
That's right. That's right. Yes.
Okay, I see.
So yeah, that's right. Yeah, exactly right. So there's an initial data set, and then you feed it into the machine learning model, and then there's a training process here, which will train all the parameters of the matrices in the machine learning model. And then after it's trained, and then it satisfies the loss function, then outputs energy and force. So there's a loss function here, and then so the training process, actually this whole thing, the training process is, so the training process is these two steps. So and then there's a loss function here, and then it will loop until the loss function converges, and then when it converges, then we feed it into MD, and then you can run MD. And then when you're running MD, you get new configurations, and then if the configurations, and then you can sample these configurations, and if they give us poor delta E, then you feed it, then you add it back into the training data set. Yeah.
Thank you.
No problem. Thank you.
Sorry, I have a quick question about the last few pages of the first part. When you talk about the yellow box of the yeah, and the output of the yellow box x 1 to n, the L plus 1 is the prediction or the input of the. I mean, it means the neighboring position, right? So it's the prediction or it's the input of the data?
It's okay. So the process goes like this: you get you feed in the atomic positions, and then this green layer will calculate Rij. Well, here he uses x1 to xn, so it's Rij, as well as some atomic some nuclear charge information. Then then all these Xij are fed into this yellow box, and then it does this continuous filter convolution, and then goes through a few other neural network layers, and then you get a new Rij, a new next layer. So it's L. This is L, and this is L plus 1. Next layer of Rij, and then you can see here he has multiple layers of these interaction blocks. So it goes from so it's input at one layer, output to the next layer, and then finally, after multiple layers, it goes through another neural network layer to model the atomic energy.
So what was the position of different layer mean? Do they mean different time for the molecular dynamics, or they mean different?
No. This is just the machine learning model. What do these different layers mean? There isn't a there isn't a very intuitive picture, a very intuitive meaning here. It's just a parameter that you can use. You can use 3 layers, or you can use 10 layers. It's of course in some of the more sophisticated models there's some angular momentum information and stuff related to it. But here in the initial work, it's just a parameter you can tune to get good convergence for your for this XL. Because XL, what happens to XL in this block? XL basically gets multiplied by WL, which is all these radial functions. So if you think of it as, let's say, in a diamond or a graphite lattice, so maybe if you go through the first block, you only capture the first ring well, and you need to go through second, third ring to capture second ring, third ring, up to the next further and further atoms, until maybe you need to go through 5, maybe 1, 2, 3, 4, 5 times for it to capture the entire image well, the entire neighborhood well. There is, in this paper they also did not explain this very they also did not give a clear or good physical meaning to this number of layers.
I see. Thank you.
Yeah, sorry.
Okay. And is there any questions? Okay, if no, that's thanks to Jian.
Thank you.
Thank you for today's talk.
Thanks for the meeting. Thank you.
Yeah, and I think we could we may arrange a discussion maybe next week. Yeah.
我有看到那个林欣老师在这里边嘛？那个林老师你好。
有的 ，Hello。
对，那个我一直请那个国靖要赶快帮我们安排一下，结果好像都还没有。那刚好你在这，也许我们尽快约个时间讨论一下，因为我觉得就说这边的工作都还蛮有趣的，然后 quantum chemistry 这边的进展其实也蛮快的。那我就想要知道说林老师，你们对 quantum chemistry 这边有没有什么想法？那我这边其实有不少 idea， 那也许我们可以讨论一下子。
可以啊。
对，好，那也许我就说今天我发个 email 给你，那看看我们的时间怎样？也许我们两个可以先聊一下。好。
国庆我们
台湾，所以我在家的都可以。
好。
星期几？
我通常都是2、3、5的下午会比较目前来讲都是会比较有空这样子。
好的，那都可以啊。
好，没有关系的，我发个 email 给你，那我们就可以在 email 上面把时间敲下来。
好的。
好，谢谢。
谢谢。
OK。
好，那直接谢谢你哦。
好，谢谢你。
好，
谢谢。
好，谢谢。
好，谢谢。
郭靖可以留下来一下吗？不好意思啊。
好，谢谢各位。
我们等一下可能还有一个会。
OK。
直线，对，我们之后讨论，对，可以之后讨论，因为我们等下就是我们还是等一下会有一个就是我们自己的 Google Meeting 这样子。
OK， 好，我是想确认一下，我们
好
星期一是不是照旧？
我们之后我们等下
好，我们之后再讨论哈。
会后再联络您看看好。好，谢谢。
好，谢谢，拜。
拜拜。